Welcome to today's problem walkthrough. We'll be diving into problem number 890, Find and Replace Pattern. This problem challenges us to identify words that match a given pattern using specific mapping rules. It's a great exercise in understanding hash maps and pattern recognition. Let's explore it together. In this problem, you're given a list of strings called words and a single string called pattern. The goal is to find which strings in the words list match the given pattern. A string matches the pattern if there is a bijection, or a one-to-one correspondence, between the characters in the string and the characters in the pattern. This means that each character in the string maps to exactly one character in the pattern, and no two characters in the string map to the same character in the pattern. The input consists of the list words, which can have up to 50 strings, each with a maximum length of 20 characters. The pattern itself is also a string with a maximum length of 20 characters. The output will be a list of strings from words that match the given pattern. For example, consider the input where words is the list, ABC, DEC, ME, EC, DKD, CCC, and the pattern is AB. The output is ME, AC. Let's break this down. The word ABC is invalid because the mapping A to A, B to B, and C to B is inconsistent. C cannot map to the same character as B. Similarly, DEC is also invalid because the mapping D to A, E to B, and Q to B is not valid for the same reason. However, the word ME works because M maps to A, and both these map to B, which is consistent and bijective. The word AC is also valid since A maps to A and both Q's map to B. The words DKD and CCC are invalid because their mappings are inconsistent. Therefore, the final output is ME, AC. Now let's consider another example. Here, words is A, B, C, and the pattern is A. The output in this case is A, B, C. The reasoning is straightforward. For the word A, the mapping A to A is valid. Similarly, for the word B, the mapping B to A is valid, and for the word C, the mapping C to A is also valid. Since the pattern consists of just one character, any single character string in words will match the pattern. As a result, all the strings in words are included in the output. Finally, there are some important constraints and edge cases to keep in mind. The constraints specify that the length of words will be between 1 and 50, and the length of pattern will be between 1 and 20. Additionally, all strings in words and the pattern will contain only lowercase English letters. As for edge cases, if words contain strings of varying lengths, only those strings matching the length of pattern can be considered valid candidates. If the pattern consists of all unique characters, only strings with all unique characters can match. Similarly, if the pattern contains repeated characters, the matching strings must have the same repetition structure. If words is empty, the output will naturally be an empty list. In cases where the pattern is just a single character, all one-character strings in words will match. Lastly, if no strings in words match the pattern, the output will also be an empty list. To solve this problem, one approach we can consider is a brute force method that focuses on mapping every character pair between a word and the given pattern. The idea is straightforward. For each word in the list, we attempt to establish a one-to-one mapping between the characters in the word and the characters in the pattern. To do this, we maintain two dictionaries, one mapping characters from the word to the pattern, and another mapping characters from the pattern to the word. As we traverse both the word and the pattern, we verify that these mappings are consistent. If at any point a conflict arises, we know the word doesn't match the pattern. On the other hand, if all characters satisfy this one-to-one relationship, we include the word in our result list. Although this approach works, it has some drawbacks. The time complexity of n*k, where n is the number of words and k is the average length of the words, is reasonable. However, the memory usage can become a concern since we need to maintain two dictionaries for each word, and the implementation can feel cumbersome and less elegant overall. To address the limitations of the brute force approach, we can use an optimized method that revolves around encoding patterns. Instead of explicitly mapping characters, we can encode both the word and the pattern into a format that captures the relative order of their first occurrences. For instance, in the word ME, the first M maps to 0, the first E maps to 1, and the second E reuses the mapping for 1, giving us an encoding of 0, 1, 1. The same encoding applies to the pattern AB, which also maps to 0, 1, 1. If the encodings match, it tells us that the word satisfies the pattern. To implement this, we define a helper function that generates the pattern signature for a given string. Then, we compute the signature of the pattern itself and compare it against the signature of each word in the list. If the signatures match, the word is added to the result list. This approach still has a time complexity of O and *k, but it is more space efficient, requiring only temporary storage for the encoding of each word. The method is cleaner, easier to understand, and avoids the overhead of managing multiple dictionaries. The strategy we chose to implement is the optimized approach based on encoding patterns. This method strikes a balance between simplicity and efficiency. By focusing on generating and comparing pattern signatures, we eliminate the need for maintaining explicit character mappings, which reduces memory usage and makes the solution more elegant. The key insight driving this strategy is that the requirement for a one-to-one mapping can be reduced to preserving the relative order of first occurrences in the word and the pattern. This realization allows us to transform the problem into a simple comparison task, making the solution not only more readable but also more efficient. Comparing this to the brute force approach, the latter offers a direct way to verify mappings but is more memory intensive and less intuitive. While both methods share the same time complexity, the optimized approach is better suited for larger datasets due to its lower space overhead. The aha moment here is recognizing that bijective mappings can be represented through encoding patterns, simplifying the problem drastically while ensuring the solution remains robust and scalable. In this problem, we are given a list of words and a pattern, and we need to identify all words that follow the same substitution pattern as the given pattern. Two words are considered to follow the same pattern if and only if there exists a bijection between the characters in the words and the characters in the pattern. This means that each character in the word maps to exactly one character in the pattern, and vice versa. For example, if the words list is ABC, DEC, me, EC, DKD, CCC, and the pattern is AB, we want to find words like me and AC where the one-to-one mapping holds. To approach this, we can use a brute force method where we compare each word in the list to the pattern. The first step is to clearly define the problem, which we've done here. Next, we iterate over each word in the list, comparing it to the pattern to check if the mapping is valid. Let's take a closer look at how we ensure these mappings are correct in the next steps. To determine if a word matches the pattern, we use two hash maps, or dictionaries, to track the mappings in both directions. The first dictionary, word_to_pattern, maps characters in the word to characters in the pattern. The second dictionary, pattern_to_word, does the reverse, mapping characters in the pattern to characters in the word. For each character pair from the word and the pattern, we check the following. First, if the character in the word already exists in word_to_pattern, we confirm that its mapped value matches the corresponding character in the pattern. If not, the mapping is invalid. Similarly, if the character from the pattern exists in pattern_to_word, we check that its mapped value matches the character from the word. If either check fails, the word does not match the pattern. However, if neither character exists in the dictionaries, we add the new mappings to both. Once all character pairs have been validated, and no inconsistencies are found, we can conclude that the word matches the pattern, and we add it to the result list. After processing all words, we return the list of matches. The solution relies heavily on the bijection property, which ensures that each character in the word maps to one and only one character in the pattern, and vice versa. This one-to-one mapping is what makes the pattern matching consistent. The use of two dictionaries is crucial here, as it allows us to efficiently track these mappings in both directions. Additionally, this approach enables early termination. If we detect any inconsistency during the mapping process, we can immediately discard the word and move on to the next one, saving computation time. In terms of data structures, we use two dictionaries, word_to_pattern and pattern_to_word. These provide constant time complexity for insertions and lookups on average. Finally, we maintain a simple list to store words that match the pattern, which we return as the output. Now let's analyze the complexity of the algorithm. For time complexity, let n be the number of words and m be the average length of a word. Checking a single word against the pattern involves iterating through its characters, which takes m. Since we perform this operation for each of the n words, the total time complexity is n*m. For space complexity, we use two dictionaries for each word, which together require O(m) space for storing the mappings. Thus, the overall space complexity is O(m). To illustrate, let's walk through an example. Consider the input where words equals ABC, dec, me, ac, dkd, ccc, and the pattern equals ab. For the first word, ABC, we attempt to create mappings. A maps to a, B maps to B, but C also maps to B, which is inconsistent. So, ABC is not added to the result. For the second word, me, we successfully map M to A and E to B, confirming a match. Me is added to the result. Let's continue with the next word. For the word ac, the mappings are similar to those of me. A maps to A and Q maps to B, with no inconsistencies. Thus, ac is added to the result. After processing all words, the final output consists of the words that match the pattern. In this case, the result is me, ac. This demonstrates how we iteratively validate each word against the pattern using the bijection property and efficiently construct the output list. By ensuring a one-to-one mapping and leveraging early termination, this approach provides a clear and efficient solution to the problem. This implementation solves the find and replace pattern problem by encoding both the pattern and each word in the list using a bijective mapping. The encode function generates a unique encoding for a string by assigning consecutive integers to its characters as they are encountered. This ensures that strings with the same substitution pattern produce identical encodings. For each word in the words list, we compare its encoding to the encoding of the pattern. If they match, the word is added to the result list. This approach ensures correctness and is efficient, as each word and the pattern are processed in linear time relative to their lengths. Here, we start by importing the necessary Java utilities and defining our solution class. The goal is to identify words that match the given pattern based on their structure. To achieve this, we implement the find and replace pattern method. First, we encode the pattern into a unique structure using a helper function called encode. This encoded version of the pattern serves as a benchmark. Then, we initialize an empty list called matching words to store words that fit this structure. For every word in the input array, we encode it using the same helper function and check if its encoded structure matches the encoded pattern. If it does, we add that word to the list of matches. Finally, we return the list of matching words. The key here is the encode method, which ensures that the structural pattern of characters is consistently represented. Let's now look at how the encoding process is implemented. The encode method converts a string into a unique structural representation. Inside this method, we use a map to associate each character in the word with a unique integer code. The next code variable ensures that new characters are assigned sequential codes, while the putIfAbsent method ensures that characters already seen retain their original code. As we iterate through each character in the word, we append its code to a string builder, separating each code with a delimiter, such as the hashtag symbol. This delimiter prevents ambiguity between multi-digit codes and ensures clarity in the encoding. Finally, the method returns the fully encoded string, which is used to compare structural patterns. This encoding process is what allows us to match words to the given pattern efficiently and accurately. To solve this problem, we start by defining the encode function. This function takes a word as input and maps each unique character in the word to a unique integer based on the order of its first appearance. The result is a tuple representing the encoded pattern of the word. For example, we use the encode function to process the given pattern ab. Initially, we set up an empty mapping for characters to integers and a variable next_code to track the next available integer. As we process each character, we add it to the mapping if it hasn't been seen before and assign it the current next_code, incrementing next_code afterward. For ab, the first character is mapped to 0, then b is mapped to 1. When we encounter b again, it's already in the mapping with the value 1, so we reuse that. The final encoded pattern for ab is 0, 1, 1. Now, we move on to processing each word in the list words using the encode function. For the first word, ABC, we start with an empty mapping and assign 0, 1, and 2 to a, b, and c, respectively, resulting in 0, 1, 2. Similarly, for dec, we assign 0 to d, 1 to e, and 2 to q, resulting in 0, 1, 2. For me, the encoding assigns 0 to m and 1 to e. When E is encountered again, we reuse the mapping, giving 0, 1, 1. The word ACK is encoded similarly, resulting in 0, 1, 1. For DKD, we assign 0 to D, 1 to K, and reuse 0 for the second D, giving 0, 1, 0. Finally, for CCC, all characters are the same, so we map Z to 0 repeatedly, resulting in 0, 0, 0. Now, we compare each encoded word with the encoded pattern 0, 1, 1. The matching words are me and ACK, so the output for this example is me, ACK. In the next example, we are given the pattern ABC and the list words equals XYZ, YZY, ZBB, AA, ABA. First, we encode the pattern ABC. Starting with an empty mapping, we assign 0 to A, 1 to B, and 2 to C, resulting in the encoded pattern 0, 1, 2. Next, we encode each word in the list. The word XYZ is encoded as 0, 1, 2 because its characters follow the same order as the pattern. For YZY, the encoding assigns 0 to Y, 1 to Z, and then reuses 0 for the second Y, resulting in 0, 1, 0. The word ZBB is encoded as 0, 1, 1, as Z maps to 0 and B to 1. For AA, both characters are the same, so we get 0, 0. Finally, ABA is encoded as 0, 1, 0. From these, only XYZ matches the encoded pattern 0, 1, 2, so the output is XYZ. Here, we look at another example with the pattern Z and the list words equals A, B, C. First, we encode the pattern Z. Since it consists of a single character, we map Z to 0, resulting in the encoded pattern 0. Then, we process each word in the list. The word A is encoded as 0, because it also consists of a single, unique character. Similarly, B and C are both encoded as 0, since they also contain just one unique character. Comparing these encoded words to the encoded pattern 0, we find that all three words match. Therefore, the output for this example is A, B, C. To summarize, the key idea in this solution is to use the encode function to transform the pattern and each word into a comparable form based on the order of unique characters. This allows us to directly compare the encoded representation of the pattern with the encoded representation of each word. By iterating through the given list and encoding each word, we can easily identify which words match the pattern. This approach is efficient, leveraging a mapping process to ensure that the comparison is straightforward and consistent. The time complexity of the find and replace pattern function involves two primary components, encoding the pattern and iterating through the list of words. To begin with, the encode function processes each character in a single word using a loop. For a word of length m, this loop operates in O(m) time. Since dictionary operations like checking if a character exists or adding a mapping have an average time complexity of O(1), the overall time complexity of encoding one word is O(m). Similarly, encoding the pattern, which is of length m, also takes O(m) time. When we move to iterating through the list of words, let n represent the number of words in the list. For each word, the encode function is called and processes the word in O(m) time. After encoding, we compare the encoded word with the encoded pattern, which also takes O(m) time due to tuple comparison. This means processing a single word requires O(m) plus m, which simplifies to O(m). For all n words, the total time complexity becomes O(n*m). Combining this with the time to encode the pattern, which is O(m), the overall time complexity of the function is O(n*m). Now let's analyze the space complexity. The encode function uses a dictionary called mapping to store unique characters and their corresponding codes. In the worst case, this dictionary will hold all m characters of a word, so it requires O(m) space. Additionally, the function creates an encoded list to store the encoded representation of the word, which also has a length of m and hence uses O(m) space. Therefore, for a single word, the encode function utilizes O(m) space. On top of this, the result list stores the words that match the pattern. If all n words match, the result list will contain all n words, each of length m. This requires O(n*m) space in the worst case. The overall space complexity is determined by the dominant factors. While the encode function uses O(m) space, this is reused for each word and does not scale with the size of the input. Instead, the dominant term is the space required to store the result list, which is proportional to the number of words n and their length m. Thus, the overall space complexity is O, n asterisk m. Comparing this approach to a brute force method, the naive solution would involve nested loops to check character mappings, resulting in a higher time complexity of O, n asterisk m squared. By utilizing the encoding approach, we reduce this to O, n asterisk m by transforming the problem into an efficient tuple comparison. In terms of best, average, and worst case scenarios, the complexity remains consistent at O, n asterisk m. In the best case, all words in the pattern are very short, minimizing processing time but still adhering to the O, n asterisk m complexity. In the average case, word lengths vary, but the overall complexity is still determined by the number of words n and the average word length m. Even in the worst case, where both the words in the pattern are as long as possible, the time complexity remains O, n asterisk m, though the constants involved may increase. Mathematically, we see that encoding the pattern takes O, m, and iterating through n words to encode and compare each contributes O, n asterisk m. Adding these together confirms the total time complexity is O, n asterisk m. Similarly, the space complexity is dominated by the result list, requiring O, n asterisk m, space in the worst case. One of the most common mistakes when solving the find and replace pattern problem is not properly handling non-bijective mappings. This happens when you assume that mapping from the pattern to the word is sufficient, without checking the reverse mapping from the word back to the pattern. For example, with a pattern like ABA and a word like XYZ, if you only check one direction, you might incorrectly allow both A and B in the pattern to map to the same character in the word, which breaks the bijection. Another frequent issue is ignoring edge cases. For instance, you should consider situations like an empty pattern or words, single character patterns, or cases where the lengths of the pattern and the word don't match. Additionally, it's important to avoid confusing character indices with actual character mappings. For example, it's not enough to simply compare whether the first it in the pattern corresponds to the first X in the word. You need to ensure that this relationship holds consistently throughout the entire pattern in word. Now, another pitfall to watch out for is inefficient implementations. Using nested loops to compare each word with the pattern can lead to quadratic or worse time complexity, which will be too slow for large datasets. Instead, leveraging hash maps can reduce the complexity to O, n asterisk m, where n is the number of words and m is the length of the pattern, making your solution much more scalable. It's also important to avoid hard-coding solutions for specific cases, such as adding if-else branches for particular patterns or inputs. These approaches are brittle and won't generalize to other test cases. From an interview perspective, this problem is an excellent opportunity to demonstrate your understanding of bijective mappings and the use of hash maps or sets. Be sure to clearly explain how you check both the forward and reverse mappings. Additionally, discuss how your solution scales with larger inputs and why your approach is efficient. If the interviewer modifies the problem, like introducing partial matches, show that you can break the problem into smaller, solvable parts. Finally, hash maps are a critical tool here, so be ready to explain their role in your solution, even though handling collisions isn't a concern in this specific context. This problem is closely related to others on LeetCode, such as isomorphic strings, problem 205, word pattern, problem 290, and group anagrams, problem 49. Each of these problems has overlapping concepts, such as checking mappings between two datasets or grouping based on patterns. Exploring these can deepen your understanding of pattern matching problems. Regarding alternative approaches, one option is the index mapping approach. Here, instead of explicitly using hash maps, you encode the indices of each character in both the pattern and the word and compare these index patterns directly. This eliminates the need for hash maps but may feel less intuitive to implement. Another approach is sorting-based, where you sort characters or words and compare their sorted patterns. However, this method introduces additional complexity with a sorting cost of O, m log m, and doesn't handle all edge cases effectively. While these alternatives can be interesting, hash maps remain the most efficient and robust solution for this problem, especially when dealing with bijections. Great work! To recap, we solved the find and replace pattern problem using hash maps to track bidirectional mappings. We explored its time complexity and key takeaways for mastering similar problems. Thanks for tuning in, and don't forget to like, share, and subscribe for more. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!